I love it. Ice cream life? Cool. My older kid does not like ice cream, decidedly. It's just like, I don't get it, don't like it. It's pretty wild. Okay. Sound. Okay, good. It's quieter than I expect. Hello, hello, hello. Sound, sound, sound. Hi. Okay. All right, let's get going. So last time, I was going to remind you that we did a bunch of algebra, and we had this whole thing where we were trying to figure out the variance of the fixed point distribution, and you may remember we spent so much time eventually finding that 1 plus this thing was just 1 plus 1, which was 2, and ultimately found that the variance of the fixed point distribution was 1. Okay, that's where we ended. What I wanted to do now, as we're picking up, is to reflect on what I think were the most important parts of the problem-solving technique, which you've also seen in discussion. But I want to note that because we often decompose random variables into, say, a sum of indicators, then what we'll often do is that when we get to a variance calculation, we'll find ourselves having to compute the expectation of products of these indicators, just because to compute the variance, I need to find the expectation of the square of the random variables, and if I have sums of indicators, we get these cross terms. And as we saw in the previous lecture, the expectation of the product of two different indicators was the same thing as the probability that two of the indicators are 1, which is the same thing as the probability that one of them is 1 and the other one is 1. Okay? And the reason that was true, if you may remember from that question, is that there's 4 possibilities for the indicators, and 3 of them include zeros. So they're just going to be 0. And then the final one is going to be 1 times 1 times this probability. And so you should know this fact well, because it's going to be handy throughout the class. All right. OK, so I had one more example from the last lecture, which was about geometric and Poisson random variables. That was that if x is geometric, then the variance, as given in the notes, is 1 minus p over p squared. And if x is Poisson, then its variance is also just the usual lambda. I'm not going to prove those. Those facts are in the notes. I think the proof for the geometric is kind of fun. It's got a nice algebra trick to it, but I don't really want to do a bunch of algebra. I want to talk about broader and more important themes. Okay. And one more that we will talk about is the uniform distribution. We haven't seen this before. But it's a really simple distribution, which is just, it's like a die roll. Takes on values from a set with equal probability, and that set's always 1 through n. So if I have the uniform distribution with parameter 6, then you either get 1, 2, 3, 4, 5, or 6. The notes give the mean and the variance without proof. They're very straightforward to compute. So the expected value of x for a die roll is n plus 1 over 2. So I have this on the board over here, because I'm going to use it later. That the expectation of a 6-sided die is 3.5, and a 20-sided die is 10.5. Okay, so just remember those. And we know that those expectations, right, they're not values that can actually come up on the dice. That's the expectation of the die rolls. Okay. And again, I'm not going to prove here. I just want to make sure that you know that that exists. Okay. All right. Any questions about any of this sort of wrap-up stuff that we didn't quite get to last time? All right. Let's talk about sums of random variables. So in a previous lecture, we saw that some random variables play nicely, like Poisson random variables. If you have 2 Poissons that are independent and you sum them, then the resulting sum is also Poisson, and you just sum their averages. And this makes some intuitive sense, right? Like if I have 2 independent objects emitting radiation at a certain rate, and we sum how much radiation we get from them, it should be just the same as if you had one radiation source that was radiating twice as quickly. Okay. And so in general, though, while Poisson is nice, other random variables, things get messy when you sum them together. Like it's a very notable property that 2 Poissons give you a Poisson. But it's not true for other types of random variables. So for example, if we had 2 binomials with different probability of heads, the result is no longer a binomial. Like if you're trying to add that you have one coin that comes up heads 50% of the time and the other 30% of the time, and you run a bunch of trials where you're adding up their heads on both coins, you get something that's just not a binomial anymore. As another example, let's consider rolling dice. I'm rolling some fair dice, and you've seen this kind of progression a little bit before, but if I roll 1 die, it's a uniform distribution where I get an equal chance of having 1, 2, 3, 4, 5, or 6. If I roll 2 dice, well, now there's some things that are more common, like 7 is the most common thing. There's many ways to get a 7, and there's not very many ways to get a 12. There's only one way to get a 12. So you roll a 6 twice. If you roll 3 dice, you get another shape, and if you roll 4 dice, you get yet another shape. Okay? And what you see is we're going from a uniform distribution to something that looks smoother and rounder and more Gaussian, as we'll talk about in a couple lectures. Okay? Now, there is a mechanical operation you can apply to these distributions to get from 2 dice to, or like if you take if you take 2 rolls of a single die and you want to compute this, this is a convolution. And that's an operation that you'll see in like a signals and systems class if you're EE oriented, but also you see it in probability because it's the natural operation for combining these functions, these distributions here. Now, one thing I'll observe is that as I sum more and more dice, the expectation goes up linearly. And that's not surprising, right? Like if I roll 5 dice, the expectation should be 5 times as much. And that's true because it doesn't matter if they're independent or not. Remember, that's the linearity of expectation. And then if we look at the standard deviation, we see that it goes up, but not as quickly. This is an observation that sometimes people call it, that starts to concentrate around its mean, right? So at first, it's very dispersed relatively. But then as you add, dispersed, that's a word I made up. But as you add more and more dice together, your mean is increasing. And the distribution starts to get more, it gathers around the mean, basically, right here. Okay? So this distribution, this concentration property, ends up being pretty interesting. We're going to do an entire lecture about that next time. I'm not going to talk too much about it today. But what we see is that the standard deviation grows relatively slowly. It's a neat property. Okay. What you can show is that this the exact rate at which we go up, or the exact function that gives me the precise standard deviation is just about 1.7 times the square root of n, or the variance is 2.9 of n. It's just the square of this. Okay? Now, while we can't concisely say something about this distribution, right? Like the exact distribution here is a little messy. I can't just say, oh, it's distributed as like something simple that we've seen before. We can reason about the expectation and the variance in relatively simple ways. And that's basically anytime you take 2 random variables, combining them and getting the exact distribution can be a mess, but it can be sometimes easier to think more about just the expectation and the variance. Expectation's really easy, right? We already know that the expectation of the sum of 2 random variables is just the sum of their individual expectations, and that's true no matter how these random variables are related. But there's another question, which is what about their variance? Do we have linearity of variance? Like what happens with variance? Okay? Well, we saw empirically with dice that rolling 4 dice gives us 4 times the variance, or 2 times the standard deviation. So let's think about that a little more. Okay. So I'm going to make a claim that if x and y are independent, then the variances do indeed combine in a nice way, that we get linearity. But there's a caveat now that we need independence. With expectation, we didn't care about independence, but with variance, we do. Okay? So I'm going to make this claim that the variance, if they're independent, is just going to be the sum of the individual variances. And that's where we saw the variances scaling up linearly as we went up in the number of dice we rolled. And of course, the standard deviation went up at the square root, which is slower, which is why we get concentration. Okay? So how do we do this? So what I'm going to do is I'm going to say, what is the variance? I'm going to just plug it into our usual variance formula. Remember, there's 2 ways we write the variance, and this is one we derived last time. So I'm going to say the expected value of x plus y. So I should know x plus y is a random variable. So if you take 2 random variables and you add them together, you also get a random variable. So we'll say, okay, we need the expectation of that random variable squared minus the square of the expectation of that random variable. Okay, now we'll do some algebra. It's not the most exciting thing, but we shall. And so I'm going to take this right here, and I'm going to square it out. So x times x is x squared. We get the cross term 2xy, and then we get y squared. Okay, now we can apply linearity of expectation, and we don't care if there's any kind of dependency between these, and I get 3 terms here. I have the expected value of x squared, the expected value of y squared, and then we have this product here. Okay? So that's, if we think about this other part right here, the other part of our equation. Okay, so what happens there? The expected value of x plus y, I can apply linearity of expectation. So all I'm doing right here, this right there is what I'm doing on the left, and I'm taking this right term, and I'm thinking about them independently, and then I'm going to subtract them later. Okay, so if I apply linearity of expectation here, do you agree with me? Hopefully I get expected value of x plus expected value of y. Then if I square this out, I get this expression. Okay, not the most exciting stuff, but I end up getting these two expressions. These are expanded out versions of this left expectation and this right expectation squared. Okay, so now I'm going to write out there. So if I actually expand them out, I have this on the left, okay, and this on the right, and I'm subtracting this one. And then I'm going to group the red terms. So I do expected value of x, the expectation of x squared minus the expectation of x squared. Okay, sorry if you're a captioner. Then I take these two terms, and I have this left cross term minus this right cross term. And then right here I have the yellow terms. Okay, I keep going, and I note that this right here is just the variance of x in red. And that's why I made it red, because these two terms, when you subtract the one on the right from the one on the left, I get the variance of x. And on the right, I have the variance of y, and I'm left with this middle term. Okay. Any questions about this algebra or anything I did here? I will note something interesting. I don't know how universal this is, but I know that I talked to a student after class a little while ago, and they were saying, compared to Manuel lectures where we're writing, it's harder to pay attention to these kind of parts of lecture. And then on the survey, by the way, if you have comments about lecture, please put them in the anonymous survey. I'm very curious to read them. But when I did my first lecture on counting, there were a couple people who were like, Manuel is the GOAT. I love the writing on the board. Manuel doesn't just read off the slides, you know. And I hope it doesn't feel like I'm reading off the slides, but maybe it does. You know, 70 is a new type of class for me to teach, so please let me know. And actually, I just bought a pen inspired by the 3 people who complained. And I don't mean like in a bad way, but I bought a pen, and maybe in 2 lectures, I'm going to try and do a more heavily iPad lecture. But it's going to take me some time to think about. So I'm going to experiment. If you're thinking, I'll give you some A/B testing, and you can let me know what you like more. To me, there seems like good trade-offs, but maybe I would be super bored watching somebody do this. I don't know. All right. Okay. So what we've shown so far is that the variance of x plus y is the variance of x plus the variance of y plus this thing in black. So what is that thing? Well, I said that if they're independent, this is going to disappear implicitly, right? I told you that variance is linear if the variables are independent. But here we're left with this term. So we're going to do a little detour here to show that if our random variables are independent, that this thing is indeed 0. And I find this proof a little annoying, like this little subproof, but so it goes. Okay. So what I want to try and convince you is that if x and y are independent, then the expectation of their product is equal to the product of their expectations. So how's the proof going to go? Okay. So this first line, let's think about what's here. The x times y is just a random variable, right? You take you have x and y, you multiply them together, you get a new random variable. And what values can it take on? Well, it can take on any product of whatever x gives you, that's A, and whatever y gives you, which is B. Okay, so whatever those combinations are, there's all these different things that x and y could be, and we're just going to consider every possible pairing, A and B. And so we're going to say A times B, that's what xy is equal to, right? Because I'm just using the formula for our usual expectations. So these are all the values that xy can take on, okay, each of these combinations. And then, because it's an expectation, we take each of those products, and we multiply it by the probability that I get that particular combination, right? So if A is 3 and B is 7, then I'm going to have 21 as part of my expectation. Then I'm going to multiply that by the probability that x is 3 and y is 7. Okay. All right, great. Now, because these random variables, if they're independent, what we can say is that the probability that x is 3 and y is 7, or x is A and y is B, is just the product of those individual probabilities. That's how we define independence. So if they're independent, we can now separate these out. Okay. Now what we're going to do is just say, okay, we're going to add some parentheses. I'm going to put the A together with the probability that x is A, and B together with the probability that y is B. And I end up with this right here. Okay, so I brought these together. And once I've done that, I have neatly on the left, this is just going to be the expectation of x. And this on the right is the expectation of y. If you'd like, here is a little like tiny example to convince you that this is really sensible. So imagine I'm rolling a 4-sided die and a 6-sided die. Okay. So if I want to start writing the expectation of the product of a 4 and a 6-sided die, one of the terms, if I expand this thing out into all the different 24 terms that exist, one of the terms will be 2 times 5, and that's times the probability that d4 is 2, that d4 is 2 and d6 is 5. Because the die rolls are independent, we can actually separate these out into 2 separate probabilities, one for the probability of die roll 4, and one for the probability of the 4-sided die, and the other of the 6-sided die. At that point, I have 2 times 5 times 1/4 times 1/6, and then I'm just bringing together the 2 and the 1/4, and the 5 and the 1/6, and then just repeating that over all the combinations. Algebra. Okay. So if indeed these are independent, we cluster together the terms, and we see that the expectation of the product is the product of the expectations. Okay. So if they're independent, then this part in the middle, that is just going to become 0, because this right here is equal to this right here. Okay? And so we're left with just the sum of the variances. Yeah. Oh, yeah. B is supposed to be under, yes. No, this is very weird looking. Yes. Right, there should be, but I can't fix it easily. Okay. Yeah, it was a typo. Okay, sorry. See, that's what happens when you read the algebra off the slide, but I want to try and fix it right now. Okay, so point for those who said I'm reading the slides, because I would have looked at it more carefully if I was writing. Okay. All right. So if we have in random variables that are independent and identically distributed, so if we have a bunch of random variables that are all from the same distribution and they're independent, we can also say that, the sum of them, if s equals x1 plus x2 all the way up to xn, then we have the following. This is just an extra additional useful property, that if we have x summed together, the expectation of their sum should be n times the expectation of x. That the variance of s is n times the variance, and that's because they're independent. So we get that linearity of variance property because they're independent. And so, for example, if we roll n 6-sided dice, we have that the expectation of s is 3.5n. That's that formula I have over there. That's always 3.5. And the variance, which we didn't show in class, but I said that the notes cover, is 2.92n. And the standard deviation is just the square root of this. Okay? So if you have independent random variables, the variances add up nicely. Okay. So summarizing what we got in this lecture, the most important things that we had, I'm just going to repeat this very end part, just these last couple bullet points, is that in general, the variance of x plus y is this expression, which is the sum of the variances plus this in the middle. If the random variables are independent, then with that typo, that slide with the typo, we have that these two expectations are equal, or sorry, that the expectation of the product is equal to the product of the expectations, and therefore this goes to 0. So now let's talk about what happens if we are not independent. Okay. Let's just continuing along. So last time we showed that, and what we just did, is that the variance of x plus y is this expression just shown. In the middle, we have this blue term, and this one I will fix because it's easy. I don't know how that happened. I remember fixing that specifically. Okay. All right. So if x and y are independent, then these blue terms cancel out. But if they're not independent, the sum is going to depend on that term, and this term is going to be called the covariance minus the 2. So it's actually this right here is the 2 times covariance. Okay. So the covariance of two random variables, x and y, is defined as the difference between the product, or the expectation of the product, minus the product of the expectations. And so we already know some things about the covariance. One of them is that in general, the variance of the sum of two random variables is just the independent variance, or the separate variances, plus 2 times the covariance. And that if they're independent, the covariance is 0. And as we'll see later, the converse is not true. 0 covariance doesn't necessarily mean you're independent, but if you're independent, there is no covariance. Okay. Yeah. Because it describes how much you expect y. So the question was, why is it called covariance? It says how much you expect y to change if x also changes. Like, how do they vary in the same direction or not? And how much do they vary in the same direction? Yeah. It could be negative as well, as we'll see. Yeah. Okay. So let's see some examples. Just a couple of small ones. Suppose we have a playing card deck and we draw 2 cards. And I'll make up an event called R1, which is 1 if the first draw is a red card. It's a heart or a diamond. And B2 is, I've drawn 1 card, I'm left with only 51, and now I'm drawing the second card. And B2 will be the event if the second draw is a black card. Now, of course, these are just random variables, and so I want to know what is the covariance that I get of these events here. Right? So what's the covariance of R1, B2? Well, that's just going to be, by definition, the expectation of their product minus the product of their expectations. So what is the expected value of R1? Well, that's going to be half, right? I expect that on average I get, it's a Bernoulli, right? It's a 50-50 chance that I get a red card. So it's a half. And same thing, too, with B2. Like, if B2 is done in isolation, then the expectation that I have a black card is going to be a half. But what happens if we want to talk about the expectation of their product? Okay. Well, R1 and B2, I said they're random variables. What kind of random variable are you? They're indicators. They tell you, did I get a red card as my first draw and a black card as my second draw? So if I want to find the expectation of their product, I need to do the same thing we did with the fixed point distribution. So all the possibilities is that it could be that the first card is not red, and it could be that the second card is also not black. But you'll notice that because I'm doing the product of 2 indicator variables, we again have the situation where 3 of the terms are always 0 because they involve zeros, and only 1 is left. So this is the exact same pattern that you saw in discussion worksheet. And then we also saw with the fixed point distribution, where just 1 of the terms survives out of the 4 combinations of these 2 indicators. Okay? So this is just that as before, just 1 of them exists. And so the question is, what is the probability that R1 is 1 and B2 is 1? Okay, that's what we're left with. Okay? So what is that probability? Think about it for a second before I reveal the secret. So now we're thinking about it. It's a joint distribution. It's the probability that the first card we draw is red and that the second card we draw is black. Okay, well, yeah, I think that's right, exactly. So we use the product rule, and we'll say that it's the probability that I get a black card if the first one is red times the probability that the first card is red. That's one way to write it out. So that's 26 51st times 26 52seconds. Okay? It's one way to write it. Because it's slightly more likely that the second card is a black card if the first was red. Okay? So the overall probability of this event is 13 51st. Okay? So those are our 3 different expectations. We have the expectation of just this single indicator is a half. This single indicator is a half. But the expectation of their product is 13 51st. And so the covariance is just going to be the difference between the expectation of their product minus the product of their expectations, and we're left with 0.0049, some number. Okay, so what does this number mean? Well, it's positive, which means they tend to move together. That is, if the first indicator is 1, then B2 will tend to be 1 as well. Okay? Any questions about that? Yeah.
So does the fact that the covariance is very close to 0 mean that they barely move together and that they're not super far from each other?
Well, the question was what we can say about this scale. So we're using here covariance, and then the units of the covariance are a little strange. Well, I guess right here, yeah, I think the fact that the number is small does indeed mean that the covariance is small. In a little while, we'll talk about something called correlation, and we'll talk about how the scale of the covariance can be a little tricky to read. Now, in this particular case, since these are indicators, yeah, I'd say that the fact that this is small is indeed meaningful, but later we'll see that with arbitrary data or arbitrary random variables, then it's we'll need to correct for the fact that your random variables may have a radically different range. Like that is, seeing that the covariance is like 480,000 or something means nothing unless you're thinking about the scale of the overall random variable. More later. Yeah.
If they are on the same scale, though, can you say that the covariance is correlated?
if they're on the exact same scale. The covariance is not the same thing as the correlation, and we'll see why later. Yeah, it has to do with the mean and the standard deviation are of the random variables. Yeah.
Why wouldn't B2 be even independently 26 over 51? Because B2 is second draw, right? So you would assume that still one draw is taken, even if you do it like E of B2.
Yeah, E of B2. So the reason is that when we're talking about R1, B2, we're thinking about the probability. Remember, that these are jointly distributed random variables. And as a result, we're thinking about, there's like an underlying sample space of all the different draws you could ever have for all the cards, right? So it's all the possible draws of drawing 2 cards out of the deck. And the random variables R1 and B2, they're mapping some of those samples to the values 1, 1. And it turns out that if R1 is 1, then there's a slightly bigger chance that B2 is 1. Like if you were to do it in terms of sample spaces, there's just more that are going to be part of this event. Because remember, this right here partitions the entire space into 4 different events. And one of the events, this event right here, just has a different size, if that makes some sense. Yeah.
Wouldn't that also apply to the independent one? Like just where you have E of B2 equals 1 over 2. Yeah.
Right. So this is now marginal. This is basically saying if we're only considering second draws, we don't know anything about what the first draw was. We don't know if it was red or not. So if we don't know it was red or not, we don't have any extra information. This one's definitely a half.
But regardless of whether but it's still like one less card, right? Because we know that there was a first draw. We don't know what it was, but we know there was one less card. Right?
Well, it's not that there was one less card, because we're not thinking about that first one. It's just like if I had a whole bunch of cards and then I said, go ahead.
Well, even if there was one less card, it's still 50-50 that it was a red.
Right, that's exactly what I was thinking. Yeah, even if there's one less card, it's still 50-50 whether or not the first one was red or not. Right. Yeah. Yep. Hope that helps. Okay. But this is a subtle point, right? So you should really convince yourself this is indeed 1/2, and this is 13/51. And if it's not clear, think carefully about it. Okay. All right, another one. Let's say we have 2 indicators. One that's R1 is the first card's red, and the R2 is the second one's red. First, I don't know. What do you expect this covariance to be, if you had to guess? So it's a similar problem to before. It's just saying if the first draw was red, and that's R1, and the second draw is red, that's R2, do we expect these 2 indicators to be positive or negative covariance? Negative, right? Okay, yeah. So if the first draw is red, is it more or less likely the second is red? Should be a little less likely because, right, like you've already used up one of the reds. So you can indeed do that math, and I can show you, and you can calculate this later after class if you want. The expectation of the product of R1 and R2 is 25 hundredseconds, and therefore the covariance is just going to be that number minus a quarter, which gives me negative 0.0049. And again, this means that if R1 is 1, well then R2 will tend to avoid being 1 as well. It's one way to think about it. Okay. Let's take this to maybe why these concepts are considered really valuable, right? Often when we think about, say, data science or data analysis or machine learning, we will imagine that our data is actually drawn from distributions, that random variables are real in some sense. And so what I'm going to say is imagine that M is the midterm score of you, the students in CS 70 in fall 2025. And it's some random variable, and I'll say as a model, it's just as real as some other distributions. And so the question is, what does M look like? Like, what are the values? So for a binomial, remember a distribution is just all the values in the range of the random variable. So if I flip 6 coins, I could get 0 heads, 1 head, 2 head, 3 head, 4 head, 5 head, 6 head. And then this is the probability that I get that particular number of heads. Okay, so I'm going to try and think about your midterm scores as a random variable. So what is A, and what's the probability of M equals A? Okay, well, let me show you what I have in mind. This is the actual distribution. Okay, so the range of this random variable, actually I should say, what is the range of A? Maybe instead of just spoiling it immediately, yeah? Right, the lowest score to the highest score, or maybe like a little more specifically, it's the set of all scores that happen. And then what's the probability of any particular score?
The number of people who
Right. So indeed, this is the random variable for your score in the midterm. So one person got 159 points out of 514 and so forth. 3 people got a 52, and that's my random variable that describes how you did. Okay. And so I can imagine, if we want to get a little like philosophical, it's like, okay, well maybe that's like this underlying like process, that like is eternal, that this is just 514 samples of, and like if I were to get more students, like maybe like I would expect to get more 3s and not as many 53s and so forth, or maybe not, but I don't want to go into Bayesian frequentist, maybe some other time. But we can imagine like M is some random variable that really exists, and you happen to be some samples of it. And this is an approximation of that true random variable. Okay. All right. Question for you. It's a little interesting. Remember that random variables are functions, and they take sample points, and then they give you real numbers. What is the sample space here? Like, what is it? Like, what's the domain of M? Curious what you think. I'm getting a call. I'm not answering it. Okay. The sample space is the domain of the random variable. Okay. The most popular answer, which I'll tell you is wrong, is it's the range of the possible scores. Oh, and also, I think, let's see, did I fix the number? Yeah, I did. Okay, this question's a little philosophical and weird. Okay, so remember what the random variable does, x, is it takes a sample, and it gives you back something from the range. So maybe it gives me 136.0, or maybe for a different sample, I get 158. What is this? What's it taking? Students. Kind of weird, huh? All right. Anyway, so as a random variable, it takes students and gives you their scores. We won't think too much about that, but I think of it as the set of all students. Okay, so I made up some fake names so that I don't want to tell you who scores or who. That would be a really weird power move, terrible move, illegal and cruel. Yeah, but Terrence Tao will say got the highest score. This is a function that takes the people and it gives you their scores. Okay. All right. What does this have to do with anything? Well, I was talking about variance, covariance, expectation, all that. Well, now I can start talking about like questions about the world. Like, I'm curious to know, like, let's say D is your discussion score. Okay, so how many times have you gone to discussion? This is the real distribution from this semester. So there were 11 people that have gone to discussion 0 times, 18 who've gone 7 times, and so forth. And given Terrence Tao, I have this random variable that says, okay, well, this is how many times Terrence Tao went to discussion. This is their score. And so a question like, what does it mean if these random variables have positive covariance? Check philosophically, yeah.
It means that the people who, it means philosophically that the people who go to discussion are the people who score better on midterms.
Right, it means that the people who go to discussion are the people that score better on midterms. They move together, okay? Does it tell you that going to discussion makes you do better? No. Why? What's the plausible hypothesis for why discussion might not actually be helpful?
People who actually care about the class go to discussion.
Yeah, maybe it's like selection bias. If you decide to go to discussion, maybe discussion's actually actively harmful, but the people who go are the ones who grind, so they do better. But we're tricking you into going and wasting time. It could be. Who knows? So there's a whole giant field that says I don't care just about the covariance. I want to know, did it actually help? And this is when you go into causal inference. This is entirely outside the scope of CS70, and in fact is something you don't see in machine learning classes necessarily. You might see a little bit of it, but this is more in the realm of the statistics department. We are going to talk, we'll talk a little tiny a bit about machine learning models at the very end of the class, but I do want to note that simply computing statistics doesn't tell you what caused what. There you need to now run experiments, need controls, that sort of thing, beyond the scope of our class. How would we do it? How would we compute the covariance? Just to see what the association is, well, we would need to know the expectation of D, the expectation of M, and we would need to know the expectation of the product of those random variables. Okay, so how would I do that? Okay, I'll tell you what they are. The expectation on the midterm was 107.2 points. The expectation on discussion score was 11.5, and that's just done using the expectation formula. I just took this number, multiplied by this one, added it to the next one, dot product of these two columns. And then DM I did with this code at the bottom, which you can't see exactly because this menu is on top of it. But I'm basically taking the product of each of these scores, right? So I'm taking the people's midterm score times their discussion score and computing the mean of that pairwise product. So I've joined the table, so I take your midterm score and your discussion score, multiply them together, and then compute the mean there. And I got 1,273.6. If I now plug that into our equation for covariance, I got the number 39.5, which means indeed they're positively correlated. Okay, I don't know what 39.5 means. It's a positive number. And so we'll talk about something else called correlation in a little bit. I can't interpret it directly except to say there exists a positive correlation. Okay. Now, we're like on the precipice of some challenging philosophy here about interpretations of probability that I don't want to get into so much here. But be aware that this is one reason random variables are useful, is they give you kind of a clear mathematical story for what these, like what D and M are. I can think about this in terms, and you know, when you get deeper into the machine learning someday, you'll talk about things like the bias variance trade-off, which is maybe a little bit of a controversial idea. But these sorts of ideas that there's like a interesting mapping between what you're trying to achieve and then these ideal mathematical models under the hood. Random variables can be used as a framework to explain what we mean when we say covariance. Okay. All right. Now I want to make one quick little note that the numbers I gave are a little hokey in very small ways. One, there's actually only 500. There's actually a total of 557 students in 70, but only 514 of them took the midterm. So it's kind of a big gap. I don't know how many of them are going to late drop or had exceptions or whatever. And then there's 555 people that had a discussion score of at least one. Everybody who took the midterm had at least discussion score. Oh wait, sorry, a discussion score, at least one. No, this number's not even true. I don't know what this came from. I'm confused about that one. I'm deleting it. But what I did is I made sure that I only looked at the people who took midterm, because otherwise I might run into a situation where covariance wasn't well defined if there were some people who'd already only done one thing or the other. So I just said midterm takers only. Okay. All right. So let's talk about independence and covariance. Okay. So suppose we have two random variables that have this joint distribution. I'll get you thinking again. I want you to tell me, do you think these random variables are independent? I think this is a fun little challenge. I'll let you think about this for a minute and make sure that this is working. Okay, yeah. Good luck. So this is a jointly distributed pair of random variables. Yeah. So x could be minus 1, 0, 1. That's the range of x. And y could be minus 1, 0, 1. And these are the probabilities of the combinations. If you're not sure how to solve this, merely knowing that the answer is solvable looking at this table is probably useful to you. Okay. No, they're not independent. And the reason is, if you knew something about one value, it would tell you about the other. So for example, if we know that x is 0, so if x is 0, yeah, y could be anything, right? There's an equal chance that it's anything. But if x is 1, we know that y is 0, okay? Or in terms of specific probabilities, if we said, what's the probability that x is 1 and y is 1? That's 0, which is not the same as the probability that x is equal to 1 times the probability that y is 1. So there's two ways of thinking about it. One, you can plug in a particular pair of numbers. The other is you can just say, if I already knew that x is 0, there's an equal probable chance that y takes on any value. If I know x is 1, then I know that y is definitely 0. Okay? What's the covariance of this? Okay. This is a good drill. I'll let you think about it. How would I compute the covariance? I'll write it on a piece of paper for myself and see how long it takes me, and that's how long I'll give you. Although I have to find a pen. Okay. It's a little bit of a trick here. Okay, let's see how it's going. All right. Okay, a little bit of a trick to this one. So the expectation of xy is 0, and the reason that's a little tricky, but at least one of the variables is always 0. If you look at this distribution, the way the probabilities are laid out, you know that at least one of them is 0, because the probability that both of them are one of these values in the corner, the non-zeros, right? So the probability that y is 1 and x is minus 1 is 0. Like these four corners are the only four combinations where there's not a 0. So the expectation of their product is going to be 0 because at least one of them is always 0. What about the expectation of x? That's going to be minus 1 times the fifth plus 1 times the fifth equals 0. Why don't I have, why is there no 3/5 in here? Because it's 0 times 3/5. Okay, so I didn't put that one. All right, likewise, expectation of y is 0. Okay, so this covariance ends up being 0 minus 0, which is 0. However, as we just saw, these random variables they have dependency between them. So you can have 0 covariance, but not be independent. And we'll see more examples of this later. Okay, just want to point that out. Okay. Now, if two random variables are independent, then their covariance will be 0. Okay, that's definitely true. If you're independent, covariance is 0, for sure. We already did that with algebra. But the other way around, you can have 0 covariance even if there's dependency. Here is such an example. And we'll see cooler examples that are more visual soon. Okay. All right, we're going to get to correlation soon, but before we do that, I want to introduce a handy notion called a standardized random variable once the screen comes back up. And you use this all the time, all the time. You don't call them random variables, but the basic idea is if I have a random variable which has some mean and standard deviation that are finite, then the standardized version of this, and the standard deviation is not 0, then the standard version of this random variable, or the standardized version, is just you take the random variable, you subtract off the mean, and you divide by the standard deviation. An interpretation of this is that what you get back is just a shifted and rescaled version of x, such that the expected value is 0, and the variance is 1. Okay? So I'm going to give you an example with the binomial. So I'm going to start with the binomial. And then I'm going to take the mean, subtract it off, divide by its standard deviation, and we're going to look at what we get back. Okay? So we know that if we have a binomial random variable, 4 coin flips, heads 25% of the time, then the expectation is going to be n times p, which in this case is 4 times a quarter, which is 1. Okay, so on average, flip 4 coins that come up heads a quarter of the time, we get 1 on average. And then the variance, this formula we did not show in class, but it is in the notes from the previous lecture, is n times p times 1 minus p, and we get 0.75. Okay? So if we know those two facts, then x tilde, the standardized version of x, is just going to be x minus 1 over the standard deviation, which is the square root of the variance. Okay, great. So what? Well, let me show you what you get side by side. So a binomial random variable, remember, it is simply all the values it can take on, paired with the probability of getting that value. And as a bonus, I'm also including the underlying sample space to make it very concrete what's going on. Though we don't necessarily always think about the sample space when we think about distributions. So here, this is the original binomial random variable, and this is the rescaled version. And note that it has the exact same sample space, that it has the exact same probabilities. The only difference is the range of the random variable. I'm just shifting and scaling so that the random variable's range is different. And in particular, what we end up with is that the values of the new random variable are z-scores. Right? So if you're exactly at the mean, I replace that with 0, saying that is the mean. The z-score of getting 1 head is 0. The z-score of getting 0 heads is minus 1.155 because it is 1.155 standard deviations below the mean. Okay, so if I take your midterm scores and I apply this transformation, the new random variable will just be the distribution of the z-scores. Okay? So it's a very handy idea, being able to standardize a random variable, and we'll use it for talking about correlation shortly. Any questions about this thing? Okay. So I want to show you first that the expectation of a standardized random variable is indeed 0. This is such a short and boring proof, but I'm going to do it anyway. So if I apply expectation linearly across this thing, mu is a constant, sigma is a constant, so this is just the expected value of x. The mu's cancel out. Great. How about the variance? Well, again, mu and sigma are just constants. If we take the variance of a random variable and divide it by some constant, what happens? Do you remember? I heard a sound. Yeah, it gets squared. So that's just 1 over, I pull the sigma out, and as it passes through the letters variance, it gets squared. What's the variance of x minus a constant? Well, if I take something that's wiggly and I add a constant offset, that doesn't change how wiggly it is. So that's just the variance of x. So we're left with the variance of x over the sigma squared, which is sigma squared over sigma squared is 1. Okay. And in fact, that's why we define the standard random variable this way. So I get z-scores. Okay. Question for you, second to last such question of the day. Let's suppose I have a standardized random variable, and we do not know the underlying distribution. Could be anything. What is the expectation of the square of the standardized random variable? See if you can figure out, how would I even answer this? Maybe it would have been nice to give you one more piece of information. I guess I didn't. So what? Okay. Good luck. Use your intuition. Yeah. Oh, wait, yes. I don't know why I paused there. Okay. All right. So how do we solve this? Well, we know that the expectation of x is 0, of course, and we know that the variance of x tilde is equal to, and this is the interesting trick, that actually in this case the variance is equal to just the expectation of x bar, or of x tilde squared. And that's because, of course, our variance, we just said, it's the expectation of the square of the random variable minus the square of the expectation. And since we already know that this one right here is 0, that means these two quantities are the same. So if the expectation of a random variable is 0, then the variance is just the same as the expectation of the square of the random variable. This is just 0. So we know the variance is just equal to that, and we already knew the variance was equal to 1. Okay. All right. Why did I do that? Well, we'll use it in a second. Okay. Now, I should note that this idea of standardizing random variables can be useful for a lot of purposes. One is exam distribution. So I took the exam distribution from fall 24, and I said, what's the maximum z-score that happens? So I basically took that random variable, and I mapped it into a standardized version. Then I took the max, and it was 2.82 versus 1.77. Very different distribution, these two. This one was much wider because the exam was much longer. And then the students who were super, super, super fast were able to get much higher scores. But you got boxed into only 1.77 degrees of freedom. Is that good? I think that's fine. Less stress, but I don't know. Your mileage may vary. If you're the 2.82 person, I guess you feel sad. Another reason is, well, sometimes I'm trying to build a machine learning model, and I want to train. I want to train some model. So by putting everything on the same scale, if I standardize my random variables, I get nicer numerical properties, especially if you start forming features in your data set that are big combinations of like squares of other ones. You don't want just massively different numbers because of floating point constraints. When you start applying techniques like regularization to models, something you might learn about someday, it's important that things are on the same scale. There's a trick in machine learning where you want to make sure that your model doesn't pay too much attention to any specific attribute of the data. And there's, I'm going, no, it's not even close. We can't even get there. But you can constrain your optimization and say, don't use that too much. And if you want to say don't use that too much, it's important that they're all on the same scale. Take Data 100 or CS 189 if you want to know about that stuff. And then lastly, sometimes it's nice to know sometimes it's nice to write proofs involving standardized random variables. So for example, these nice properties mean it will make it easier for us to use something called correlation in a moment. Okay. All right. So let's talk about some properties of covariance, and we'll talk about correlation, which is a nice notion. So in the previous lecture, we showed some properties of variance, like for example, the variance, which this is the original derivation. I'll restate this because I think it's important to think about where this came from. We wanted to know how much does x deviate from its mean. If we just do the expectation of x minus the expectation of x, then you get 0. That was not a good one. We did absolute value, but then we couldn't apply linearity of expectation. That wasn't great. So next we did a square. The square works pretty well, but it is a little clumsy because we have to start thinking about, for example, like cross terms of different indicators or whatever, right? Like we have to start thinking about like cross multiplications, which is a little messy. You have to deal with squares, but it's not so bad. It's not intractable. Generally works out okay. The math is fine. And that's why we ended up with this as our definition of dispersion. We use variance. Then we did some algebra in the previous lecture to show all these different properties. How about the covariance? Okay, so the covariance has some similar properties. For example, we can rewrite it as this, and I'll show that. I made a slide. I might regret it a little, but I'll just show that another way to write this. Just like variance had 2 forms that we'll often use, with covariance there's 2 forms we'll often use. The covariance of 2 random variables, if you add something to them independently, just the covariances of without the constants. And if I have the covariance of cx and dy, you get c times d times covariance xy. There's more properties in the notes, but I'm not going to use them today. But if you want, there's like the bilinearity of covariance, but so it goes. I'm just going to show you the first one real quick because we're going to use it. And you can read these in the notes or reprove them as you want. They're not very interesting. And then there's 2 extra little properties in the notes as well. Okay. So this first proof, I just have it on the slide as 1 because I want to get through this one quickly because there's nothing spiritually stirring here. But basically, if we have our original formulation for covariance up here, I will show you that I can get to it if I start from this other version, just the direct proof. So I purport that this expression here is the same. How do I do that? Well, I'm going to multiply out the cross terms. But before I do that, I'm going to replace expectation of x with mu x. Why am I doing that? Conciseness of notation. It's like nested e's get confusing. Though we will see at the very end of lecture today they're useful sometimes. Okay, now if I multiply out these cross terms, I'm left with xy minus mu y times x. Oh, guess what? Linearity of expectation is going to turn that into mu x. okay? So we end up with, you glide your way through this algebra, we get 2 of these mu x, mu y's crossing out, and or like canceling out, and you're left with just 1 negative 1. Very similar to what we saw with variance before, and this right here is just this top expression. Okay. All right. Proof by speed. All right. Correlation. So earlier we talked about how I don't really know what 39.5 means when I'm talking about the covariance of your discussion section and your midterm score. So correlation is a rescaled version of the covariance. The idea is that we have 2 random variables like your midterm score and your discussion score, and they have some standard deviations that are positive, so they're not 0. Then the correlation is going to be given by the covariance divided by the product of those standard deviations. And the reason we'll care about that is that it will always lie between -1 and 1. It's more intuitive to interpret. We're not bound to the scale of how big midterm scores are and how big discussion section scores are. And so I'm going to show you why it is the case that we're always between -1 and 1. Okay. This is a surprisingly ugly proof, actually. But I'm going to do it because, I don't know, I think it's an interesting way of thinking about the... Like, I'm just surprised there isn't a better way. Or if there is a better way that I don't know what it is. But this is the best one I know of, the one in the notes. And what I want to show you is that the correlation is definitely always locked into that range, no matter what x and y are, as long as we know that these are the standard deviations. Okay. So my little lemma here is going to say, again, let's use mu x and mu y for the expectations of x and y. Okay. And let's say x tilde and y tilde are the standardized versions of x and y. Okay, that's why I introduced them primarily. Turns out then that the correlation of x and y is just going to be the expectation of x tilde times y tilde. Okay, they have the standardized versions. Okay, so by applying this transformation, the correlation is just going to be the expectation of the product of the standardized random variables on a nice scale. So how do we prove that? So this first proof isn't so bad. That's the next part that's a little messy. So the correlation is by definition the covariance divided by sigma x, sigma y. Okay, what's the covariance? Well, I'll use this version of the covariance. That was the one I speed proved. And I'll say, okay, so we'll replace it by its overall expression, or by this expression here. If I multiply that out, and I just pull it into 2 pieces, like I think about this as x minus mu x over sigma x, and this is y minus mu y over sigma y, if I now think about this expectation here, you will see that this right here is exactly x tilde, and this right here is exactly y tilde. Okay, so the correlation is indeed the expectation of the product of the standardized random variables. That wasn't so bad. Okay, now's the part that I think is a little messier. Okay, so what I've showed so far is that the correlation of 2 random variables is just the expectation of the product of their standardized versions. Okay, so now what I want to do is I want to say, okay, well, how do I know that the correlation is definitely always between 1 and -1? Okay. All right, any questions about this? I've been talking a lot. Okay. So you got your midterm scores, you got your discussion scores, and you compute their covariance. It's some number, 39.5. I don't know what that means. Okay, well, if I divide those by the standard deviation of the midterm score and the standard deviation of the discussion score, I get a new number that's between -1 and 1. And that's going to hinge on the fact that the correlation is the same thing as the expectation of the product of the rescaled midterm and the rescaled discussion. Okay. So first I'm going to prove that the correlation is always less than or equal to 1. Okay, so what I'm going to do is I'm going to consider this totally arbitrary function of random variables x tilde minus y tilde and square that. Do you agree with me that this expectation should be greater than or equal to 0? Why? So it's an expectation of something. How do I know this thing's bigger than or equal to 0? I'm hearing that sound again. Right, so x tilde minus y tilde is a random variable. It could be positive or negative, but once I square it, it's positive. So whatever it is, it's greater than or equal to 0. Next question, why this quantity? Because it works. That's why. Okay, just you picked it randomly or like arbitrarily in order to make the rest of the proof work. Okay. So then what I'll do is I'll say, okay, well, what is this thing? Okay, expectation of x tilde minus y tilde. We square it. Okay, let's expand it out. Let's apply linearity of expectation. We're left with this. Okay. What's the expectation of x tilde squared? You guys did that earlier and got 1. This over here is also 1. Okay. The expectation of the squared is the same as the variance. It's 1. Okay, then we're left with this in the middle. Okay, what's this right here? Okay, well, that's the correlation, right? That's what we just said. Like another way to call this, another name for this is the correlation. So 1 plus 1 is 2. And this right here is the correlation. That was our lemma. Okay, and what do we know about 2 minus 2 times correlation? How is this related to 0?
Has to be greater.
Right, it needs to be greater than 0. So if this whole thing is greater than or equal to 0, what does it tell you about the correlation? Well, it says that the correlation is less than or equal to 1 because I just move it to the right-hand side, divide both sides by 2. Surprisingly ugly. But it gets you there. So basically the proof was make up some arbitrary new random variable as a difference of these, and then use that to ultimately show that, like this thing is, it includes the correlation as part of it, and therefore we can, using this algebra, get to the point where correlation is definitely less than or equal to 1. Okay, how do you show the other way? Okay, so that one's done. Now I want to show the correlation is always greater than or equal to minus 1. Proof is exactly the same thing, except that now instead of using x tilde minus y tilde, I'm going to use plus. And again, why? Thoughts? Did I lose you too much? Because it works, exactly. So I'm not going to do all the math again, but it's the same exact thing in reverse, and we get check. Okay, so the correlations between the two. Surprisingly unpleasant proof, but that's where we end up. Okay. I was talking to Umesh, who taught this class a long time ago, and said, everything in CS 70 should either be useful or beautiful. I guess this is maybe, I don't know, this might be in the category of not, I guess it's useful, but I don't know. Don't like the smell of it. All right. Okay, let's talk about correlation in general. Well, let's imagine we have random variables x and y, and what I'm showing here in this plot is a picture. Basically, imagine doing like a 2D scatter plot of samples drawn from those distributions. Okay, like imagine you got midterm score on the x-axis and discussion score on the y, and you're drawing samples from this joint distribution. If the correlation is greater than 0, then we'll tend to see a linear correlation going up. We're not going to talk about linear regression in this class. Sometimes that's covered in 70, but in semesters where there's Veterans Day on a Tuesday, there's not. Or when Alistair teaches, there's not linear regression, but you'll also see it in many other classes. So I'm not really going to get into like linear dependencies and exactly how we can interpret linear regression in terms of random variables, but these are examples of positively correlated random variables, and here are some negatively correlated. And here are some that have correlation of 0, okay, equivalently a covariance of 0. So this right here, there's no correlation, just noise. And this one right here, this is an example of dependent random variables. Why are these not independent? If you look at this thing, what's dependent about it? Give me an example of something that can't happen. Yeah, 0, 0. Like if x is 0, y could be totally not 0. Like if x is 0, y could be here, here. But when x is 0, y can certainly be 0 somewhere along this whole, in this joint distribution. But if x is 0, y cannot be 0. That tells me these are not independent. Yet their correlation is 0. And you can have arbitrarily complicated looking relationships between x and y. But if they're not a linear relationship, you're not going to pick up this correlation. It's going to come out as 0. Okay. All right. Okay, so then back to our midterm scores. If I go through, and I'm going to get philosophical again on you in a second, if I compute the correlation like so, by taking the covariance and dividing by the standard deviations, I get 0.33. And that's the expression I wrote in Python at the bottom, roughly, and I got 0.33. Here's something very interesting. Last semester, in fall 24, it was 0.32. Okay? I don't know what this means exactly, but it is interesting. Like it suggests that, I don't know, maybe there is some like underlying like fact about the universe. It's a very complicated fact because it captures everything about like students show up to Berkeley. They're this likely to go to discussion. The ones who do well like have these habits and the ones who don't have these habits. And the kind of incentives you give to the students to come to discussion affect these students in different ways. But at least between these two semesters, the correlation was, relatively steady. Or maybe it's a totally random chance. And if you study statistics, you can talk about how to avoid false discovery. But I thought that was pretty cool. The correlation was similar. So the correlation is somewhere between -1 and 1, and in your case it was 0.33. We will not talk about, like, for example, explaining some fraction of the variance or whatever else. That's not our class. Yeah, no r-squareds in here. In case you're curious, I actually also plotted the data. So this is the midterm versus discussion score for our semester. And you can kind of see this upward relationship. But on this plot, if two people have the same score, you can't see them. Like, they're just directly laid on top of each other. So it's kind of hard to see what's going on. But if I do a little bin-wise averaging, where I say, OK, all the people that had a discussion score of 5, here's 1, 2, 3, 4, 5 of them. Their average score is 87.5. You can see that it goes up over time. Okay? You get a sense that, like, students who are going to discussion more tend to have a higher average. Okay? This is not a data science class. We're not going to go into it in too much detail, but kind of fun to look at. Okay. Any questions? All right. One quick note. Let's suppose the correlation is exactly 1 between x and y. In that case, we have actually this interesting fact that x and y are really the same as each other in disguise. So if they perfectly correlate, they're the same thing as each other. They may be on slightly different scales, but we know that if we rescale them, they're going to end up being on the same. They're going to be the exact same random variable. And the reason, if we were to actually work this out, if we take this expression here, so x tilde minus y tilde squared, we showed earlier that's 2 minus 2 correlation xy. If that correlation is 1, then what we end up with here is that this entire expectation ends up being 0, because it's 2 minus 2. And since the expectation of this difference is 0, the only way that can happen is if the x tilde and y tilde are the same. Okay? The implication basically is that if the correlation of two random variables is 1, that means they're just rescaled and shifted versions of each other. In other words, you can find an a and a b such that you just shift it over and then so you scale it and then you shift it over. Okay? You can also show a similar result if the correlation is x. The correlation is exactly -1. In which case, it's the same thing, except that the a is going to be less than 0. Okay? One more thing, then. Okay, and I think this is now going to be like a handy tool. We were talking about in our meeting whether or not this is a bit of a cul-de-sac. Actually, at this point, I should say, we finished almost all of the discrete probability that we're going to do. This is the one last kind of like basic move in definition. In the next lecture, we're going to talk about concentration inequalities, where we start saying, how much can the mean and the variance, how do they behave? Like what kind of rules can we make for any possible distribution? And then we're going to talk about continuous probability. And then the last 2 lectures will be Markov chains, which are going to use a little bit of this. And then we'll talk a little bit about text generation. So conditional expectation is, some of this material is a little bit of a cul-de-sac, and that we're not going to use it so much. We'll see it a little bit in Markov chains, but we're gonna do one last little excursion in discrete probability. Okay. So we want to be able to answer this kind of question. It's an annoying question, but kind of a fun puzzle. Let's say we do a weird nested game where I have 2 dice and y, and I'm going to think about this as a jointly distributed pair of random variables x and y. Y is going to be the outcome of a 20-sided die roll. And then x is going to be the outcome of a y-sided die roll, where y is the result of the 20-sided die roll. Okay, so I roll a die, and that tells me which die to roll. Now, if it comes up 1, I mean, a one-sided die, I guess, is kind of a trivial object. I don't even know what it would be. Like, I just drop something, and if it lands, that's it. All right, and a 2-sided die is a coin. A 3-sided is a little complicated and so forth. But they're not going to be polyhedra, but let's just say we could do it. Okay, so what is the expectation of x if y is 6? It's on the board over there. So if the 20-sided die roll comes up 6, we roll a 6-sided die. What's the expectation in this case? It's the expectation of a 6-sided die, which is 3.5. You could write it all out. I wrote it on the board, so I could say, okay, there's a 1/6 chance it's a 1, 1/6 chance it's a 2, and so forth. That's 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6, 3.5. Great. All right. Or equivalently, I could have written it out as the following. I could have said, I'm going to add up over all of the x's in the range of x times the probability of getting that x, knowing that y is 6. Okay. How many different x's are there here? guess you could say 6, sure. Or maybe I'd say it's even 20. I don't know. To me, the range of x feels... Actually, no, the range of x, like literally the range of x is 20, because the second die roll could be anywhere between 1 and 20. It's just that when y is 6, what's the probability that x is 7? 0. Okay, that's the way I think about it. So the range of x is 20, or it's the integers from 1 to 20. But the probability here, if y is 6 of the big integers, is going to be 0. Okay? It's a jointly distributed random variable with these properties. Okay, that's question 1. If y was 6, what's the expectation of x? Okay, great. Let's generalize. Okay, we're going to try and go onwards and say, I don't want to just think about this dice problem. I want to think about any possible pair of random variables. Okay, so what would that look like? I'm just going to take this exact pattern and generalize, and I'm going to say that the conditional expectation of x given that y equals y is we're going to sum over all of the values that x could take on, x times the probability of x equals x given y equals y. This is generically true forever. I'm not proving it. I'm kind of introducing it as the natural definition. No, actually, I should just say I am introducing this as the natural definition of conditional expectation. There's no proof needed. It's by analogy to what we were doing before. This is what we did with die rolls, but this is the general idea. That's how we're going to define conditional expectation. Okay? Any questions about this idea? Okay. More generally then, okay, that's what I already had. Okay, I don't know why I had it twice. Next question. Let's suppose, and there's no thing to answer on your phone here, and this is just an open question. Let's suppose now we want to find the expectation of x. Okay, I did it for y, if y is 6, but now I want to know the expectation of x in general, because it is some random variable. So I want to know, like, what do you expect to get? Like, if I keep doing this over and over, roll a 20-sided die, get a 7. Roll a 7-sided die. Roll a 20-sided die, get a 19. Roll a 19-sided die. If I keep doing that and I average all of those 7-sided, 19-sided, whatever s dice, what do I get? Thoughts on how I would do this? Yeah.
The expected value of each of them is like n plus 1 over 2, like for each y.
Yeah, for each y, there's a different expectation, which is n plus 1 over 2, right?
Probably pull out the 1/2, right? And then have a sum of like,
You can pull out the 1/2, I agree, yeah.
and just sum like from like 0 to 20 n plus 1.
Right, so we could look at, but there's something we need to do with each of the expectations. So it's not enough to just add all of the different expectations.
And then divide by like 1/20.
Yeah, so we want to weight them. So there's 20 different possibilities for y, and for each of them we'll compute a different expectation. Okay, so for example, just like you were saying, if y is 2, for example, the expectation of x given y equals 2 is 1 plus 2 over 2 is 1.5. This is the general formula. Look at that for a second. So for any number of dice, so any number of sides on a die, the expectation of the roll is going to be 1 plus the number of sides divided by 2. Okay, so if I'm rolling a 20-sided die, the expectation is 10.5. If I'm rolling a 1-sided die, the expectation is 1. Rolling a 2-sided die, it's 1.5. So for each of those first rolls, the y's, you have a different expectation. And then each of those 20 possibilities is equally likely. So the expectation of x is going to be 1 times 120 plus 1.5 times 120 plus dot 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 plus 10.5 times 120. Okay, so we're summing up a bunch of different expectations, each of which is equally likely. Okay, so this is one of the expectations, this is another, this is another. Okay? I can do the math here, and I can say, okay, what does that actually come out to? Well, that's 115 is so basically if you take 1 plus 1.5 plus 2 plus 2.5 all the way up to 10.5, you get 115. I'm not showing that here. We could write out an expression. The discussion worksheet, you'll do one that's similar, so I'm not going to do it here. But I get 5.75. Just trust me that this is 5.75. Okay? This is one way to do it, and this is using this law of total expectation that I'm about to mention. Okay? So what I've got here, this is an answer, and it works, but it's a little messy. What is if I generalize this process, what's happening? Okay? So in this particular case, I'm summing up weighted expectations. So I have different expectations, 20 of them. This is the expectation of x given that y is 1. The expectation of x that y is 20. And then each of them happens with, in this particular case, equiprobable chance, right? Probability y equals 1, probability y equals 20. Okay. So more generally, that gives us, I guess I'll call this the law of total expectation. That if I want to know the expectation of x, it is simply the sum of the expectation of x given some event times the probability of that event, and then we just consider all the different events. Okay, that's basically what's happening here. So for example, one of those events here, like A20, is just y equals 20. All right, here's a terminology question I'm going to hit you with. It's not really exactly related, but I'd like you to give it a peek. Okay. So the question is, what is y equals 20? I think this stuff's important because you make your life harder if you don't, if you start forgetting the basic definitions. This is the last one of these today. All right. So the answer is these three. So it's the set of all sample points in the sample space which y maps to 20. That's its definition. So remember that random variables partition the underlying sample space into different events. Y equals 20 is all of the things in the sample space that map to 20. Okay. Now in this particular case, like what is the sample space? It's die rolls. So it's just like the sample space. This is a trivial function because it just takes like 1 and gives you back 1. But like fundamentally, that's what it does. Like if we're talking about coin flips, maybe now there's many different coin flips, sets of coin flips that add up to some number. But it's the set of all sample points which y maps to 20. It is also an event. What is an event? An event is defined as a subset of the sample space. Okay. All right. So all of these things are true. Though I guess the size of it is just 1 because there's only 20 die rolls, and like if you get 7, you get 7. So y it's like the identity function. Okay. Right. All right. Is there a question? Okay. All right. So in the context of our die rolling example, we can think about these events as defined by the random variable. A1 is the event that y equals 1. A2 is the event that y equals 2. Okay, it's just a collection of sample points in general. So we can rewrite it as follows. Because AI, right here, like I just told you that y equals 20 is an event. So instead of saying A20, I could say, or instead of saying AI, I could say y equals y. And in this particular case, y is going to be any choice from the range of y. Okay. So this right here is another way of writing this expression on top. If my events are defined in terms of another random variable, I could just say, okay, well, instead of writing AI, I'm going to say y equals y. The set of all sample points such that y equals this little y. Any questions about this? Okay, and so that leaves us to our very last thing I want to talk about today, which is this iterated expectation form of this up here. So this right here is the law of total expectation. This is what we used, that you used to solve that problem and got 5.75. There's another version which is nicer, which is iterated expectation. I'm going to show you first why it is useful, and then maybe I will prove it. We'll see. I don't know if I'll have time, but the proof is on that. But I think really what I want you to understand is actually more the why this is useful as a tool to solve bigger problems. Okay. So we know, I just said without proof, that the expectation of x is the expectation of x given y? That seems strange. Okay. Well, first we need to identify the expectation of x given y. What is this thing? I'll give you a hint. We're computing an expectation over it. So what is it? What do we compute expectations over? Or expectations of? Random variables. Okay, so it's some kind of random variable. What is its distribution? Okay, so it's a random variable, means it's a bunch of values and the probability of getting that value. Okay. What could the expectation of x given y be? Give me one example for the die rolling example. You guys might be tired. I'll show it to you. So this is the exact distribution, right? So one possibility is that the expectation of x given y is 10.5. When does that happen? When is the expectation of x given y equal to 10.5? When y is 20. When y is 1, the expectation of x given y is 1. It's kind of interesting. It's like the expectation is itself a random variable, and here's what it could be. And then lastly, how do we write the expectation of x given y in terms of y? Because I'll spoil this one too. So this on the right is the random variable y. Okay, so what could y be? Y could be 1, it could be 2, it could be 20. And the way we go from y to expected value of x plus y is y plus 1 over 2. This is the most important part of this last little piece of the lecture, which is that expectation of x given y is really a random variable. I'm talking to you video when you're rewatching this later. Notice this is a distribution, and it is exactly the same thing as y, but we've simply added 1 and divided by 2. So 19 plus 1 is 20, divided by 2 is 10. So what's the expectation of x? Okay, here's the last little trick, which is if you're using this iterated expectation, and this is deep, the expectation of x is just the expected value of x given y. What is the expected value of x given y? It's y plus 1 over 2. Well, if I apply linearity of expectation here, I just plug in the 10.5 directly here. 10.5 plus 1 divided by 2 is 5.75. Okay. So I know that's not enough to fully digest this. There's another really nice problem at the end of the discussion worksheet that will cover the same notion. But what I want you to think about is how much less annoying it was to use this compact problem at the version of the bottom versus this more expanded version of the top. And the last part, which I will not discuss, I guess,